All right, so I'm going to talk about Phoenix Blue and more, which is some of the FPGA efforts that's going on the forum. There's a group of us that are sort of working on this, about three, Exos, myself, and Igor. Many of you have seen some of the work that Igor's done with the cores, and we've been working to effectively bring boards together for the actual original ST so that we can replicate the original chipset. But let me just click on the link here. I'm totally unprepared, by the way. This is really winging it. So just to recap, on the ST, we have various different chipsets. We've got the glue, which is generalized logic unit. This is really all the sort of control for data paths, things like that. This is the one you sort of trick if you want to get your STFM to read sort of TOS 2.06. There's the shifter for video shifting. Basically does bitmap graphics. It's pretty small, 32 kilobytes of continuous memory. And there's a blitter, which basically shifts large blocks of data around. There's also the memory management unit, which basically links the blitter, DMA, CPU, and sort of does all the memory mapping and so forth. And then there's a direct memory access chip. That's for the main standard ST. As we all know, with the STE, there was sort of a combined version of that, and all the newer sort of systems had other things like the Falcon, they had VidL and all sorts of things like that. But what we're going to do is concentrate on the ones that are in red there. I really should have had this the other way around, but there we go. We're going to sort of talk. That is the custom ST set. There's more like stereo sound DMA. There's a microwire interface and various other things. I won't go into too much detail there. I want to talk about this. So the Phoenix FPGA journey, the blitter. We started this to try and get the sort of blitter core working on the standard STFM. The image you see in the top right was the first board we sort of plugged in. It was using a large sort of Max 10 large footprint chip. I think the first one we actually plugged in, it went up in smoke because the regulator footprint was incorrect in Eagle. But we sort of got it working, and we had various different sort of versions that sort of faltered for various different reasons, mostly soldering that damn BGA chip on the top. That was very difficult. In the end, we actually decided to retire this board and actually come up with more of a combined type of board to try and make it easier for us to sort of develop. So first off, before I get there, this is sort of showing the 100% getting the blitter working. So Eagle helped us to tune the core on the actual hardware. We were getting what we're sort of calling 99%, because as you can see just on the left hand side, the blitting was sort of 99% compared to original ST. There was a couple of programs that Cyprian actually provided us to help test the sort of blitter. You can see on the left hand side, those two were sort of like very sort of all over the place, and nicer sort of patterns on the other side. So yeah, the first one and I think the third one, that's the difference between the two cores that we had, and the one in the third is the actual one that's actually working correctly. So we ended up with a core that's 100% psycho-accurate, able to run on the STFM. But what we wanted to do to really make it a platform so we could start doing all the other chips, and we came up with these. So these are half the manufacturing process about a month ago. We actually have two flavors. One's called the Phoenix Blue, and the blue is a combined chip board. So you can actually run it in the BL mode, the BL part of blue, which is blitter. And then you can also run it in the glue mode, the UE mode, as a glue. So the idea is you have one board that you can actually have either one of those actually running from it. So the one on the left is actually set up as a blitter. It's just got some solder links across on one side. It's got the core for the blitter. The other blue in the middle has got the solder links on the other side, so it's the glue, and it's got a core for the glue. That ST down there is actually running the blitter board and the glue one, both of those, and it's actually running there. So you see it's actually doing that. The blitter core's in there. the glue. Eagle helped me get that glue core done within the last sort of night yesterday to get it up for this session. And the idea behind that is that we now have these boards that we can actually use. We can have the cores. We still need to work on the glue one to get it better. It's not quite 100%. There's a few things we need to do there. And we also have another board, which is the MMU. The pinout was so different on the MMU, we had to have a completely separate board. We have that board built as well. We've been using it just in sort of like testing mode to make sure the clocks are in sync and it's locking and things like that. The board seems to be working as well. We've just yet to sort of start sort of putting cores on it and actually sort of checking it out. I've just shipped these 3 off to Igor so he can start doing some more sort of work and development. But I want to go a little bit more into this, how we actually did this. And I'm sort of going to go into the schematic sort of board and the cores. I'm going to drop this a second and just go to my laptop and talk loudly. Just bear with me. So what I'm going to, you can still hear me, yeah? All right. So what I'm going to do here is first of all put my glasses on so I can see what I'm doing. But I'm going to have a look at Eagle first. So we tend to do our stuff on Eagle, and I know Exos, you'll say this is the newer version. Don't like that newer version. So this is actually the schematic that we have of the blue board, and it's actually quite simple. So we've got up in the top left corner is the socket. Yeah, so the socket we actually put into the H5 board. So it's got all the pinouts for the blitter and the glue. So we basically lined all those out. The items you see on the bottom right, they're basically translators. They are a load of chips that basically translate from the 5 volt to the 3.3 volt for the FPGA. And they're basically for every single signal we have going in. And then the core stuff in the middle is the FPGA. So they're all the different FPGA lines that we've associated to the different pins. There are some special ones there for like clocks, and then for the JTAG for actually programming the core, things like that. And then we have a few peripheral ones. You've got the power lines. There's a regulator to go from 5 volt to 3.3 volts. The jumpers on the top left, which basically allows you to switch a couple of the pins around for whether it's the BL, the blitter, or the glue side. And then we've got a couple of jumper tag, the JTAG to actually do the programming, a couple of other things for config, so you could actually have 2 cores and then switch between those 2 cores using a jumper. And then there's another one just so we've got a couple of extra I/O out if we want to actually play around with any additional things we want to do as well. And then a couple of LEDs on that. So that's actually the schematic. There's nothing really too fantastic or rocket science for this actual board. And if we have a look at the layout, again, this is let's make it a little bit better. Let's look at the top layer. So if you can see that, that's the top layer. You can see the FPGA at the top. We're actually using wiring pads, so we can actually have the pads of the BGA linked to each layer if we want to. So it's a 4-layer board, and we can do that. So you can see that you've got the sort of the solder jumper links, the pads for the actual FPGA on the top. If we go down through the different layers, we've got the next layer down. This is most of the layers coming from the translators to the actual FPGA. We then have further down a few additional ones just to bring out the IOs. This actually is one of the, I think it's the 3.3 volt plane as well when it flood fills. And then lastly, the bottom, you can see the translator chips going out to the actual socket, and also the regulator as well, and a couple of pull-up resistors networks at the top. So that's all the board is. It's not rocket science, and it sort of works. And then we use actually, before I move on, is there any questions so far? I know I'm rambling on and talk things. We actually use Quartus because we're using the Intel Max 10 chip as our sort of FPGA. I actually use Linux in a VMware session, but we've actually got not here. we're actually using here we are. Quarters here I've actually got up. This is just the actual way to program it. So you can actually see it uses USB Blaster. If you've got the core compiled, you can then just basically blow it onto the actual core. I'll see if I've actually got the rest of the stuff up here. Yeah, so we actually have, for example, this is the glue. This is actually the glue logic analyzer stuff that Igor was working with me to test it out, making sure the locks were happening and so forth. We were able to compile this and actually put it in. We were able to also run traces, which is quite a good thing that you can. I didn't think I had any saved here. It doesn't look I do. Let me explain this. This is a signal tap, and when you got the JTAG USB Blaster in on the actual board, you can run this in like a logic analyzer, so it can actually look at all the different inputs and outputs that you want to have it look at. So you can have all the address lines, read write, things like that that are actually in there, and it will actually do a trace of like a logic analyzer, so you can see what's actually happening. I thought I actually had a trace there, but I told you I was winging it. It's not there. But that's how we're actually doing this whole thing. And that's how we're sort of doing the Phoenix Blue, and if I can go back there, and the MMU. I've lost it. Was here? There it is. Okay. But why are we doing this? So we're doing this because we want to have cycle exact cores across all the chipsets that are there, the Blitzer, the glue, the MMU. We want to have that so that, one, we can replace these because they're very difficult to get hold of, and two, we can then start moving upwards. So we can take what was the original ST and start to move it into worlds that might fit, So there are things that you can do like the MMU. The MMU, you could say, well, there was 14 meg of RAM in the ST and it could address 14 meg of RAM, so why can't we turn that on? Well, you could with the MMU if you had access to the core and a few other bits and pieces. And the same with the glue and the same with the Blitzer. So we are working on another board, and Exos has been doing quite a bit of work on that in the background with Igor. And it's effectively called the Nexus. And this is really about bringing things together and starting to lift it up. And one of the goals that Exos is looking to try and do with this is be able to take the bus speed up to something like 32 megahertz, having a Blitzer run at a lot more faster rate than it is currently, expand that memory, and do many other things with this as well. And also put the shifter into this as well. So basically it's a watch this space thing, because there is more to come with this, but we want to get these cores right, working with Igor to get these done, which gives a first base for this and people to be able to put these into machines to have the original chips replaced. But then we want to take it further for that particular thing as well, as to actually do the Nexus and take it to the next level. Okay, I've winged it enough. All right, any questions, thoughts?
What are you using for the level shifting? I know that the chips that I've been using a lot to do the 3.3 to 5 are very good. They're bi-directional, but they are coming to the end of life. Have you found sort of something that can do that just as well, or are you having to trigger directions and things like that?
When you say coming end of life, are you talking about your FPGAs or the translators?
The translators, I can't remember what they are.
Yeah, I think we're using like the GTL 2010s or the 2008s, because they got like 10-bit wide and 8-bit wide. We can still get them. We're still seeing them around. So yeah, it's.
Do you have to collect your things into these ones are all going to write at the same time, and these ones are all going to read at the same time?
No. Either way. So we just mix them. It just works. Exos did a lot of sort of testing of these chips. I think there's a whole thread, isn't there, on the forum of this. We tried different ones, but these ones seem to be the best ones for doing this. Cool. Anything else? Any other questions?
Can it play Crisis?
Sorry. At the moment, the glue is that glue is just it was just a hot off the press from Eagle. We didn't even think it was going to work, and it did. If you try to run other things on it, because this board here has actually got the FPG shifter on it as well. It's not playing nicely with the glue, and it just goes off. Of course, closure is just like a dead duck, you know, when you try and run this at the moment. So there's a lot more work to do with the cores. Okay.
What additional features do you think you'll build in to put it for the rest?
I think you'll have to watch the space on that. Yeah, we need to get these right first, get it working 100% before we start thinking about tapping things onto it. But yeah, as you can see, like if you've got a core that works 100% for the MMU, that's your memory management. You can start doing some things with that as well. But it's the Nexus, I think, that will start to unlock a lot more because you're bringing them all together as well. It's almost like the new version of the GST or the whole combined thing you get with STE. Sorry.
What sort of capacity are you running these FPGAs at?
Capacity as in the size of the FPGA?
Utilization. Yeah, utilization. You know, is there a lot of room for expansion? You have a lot of overhead.
We've got the smallest one we're actually using, which is the O2. There is still some room in some. It depends on the core as well. We've also been talking with Eagle about. We've been calling them like small and larger versions of these because like you can go up to I think it's the 32 or the 16 version. They've got a lot bigger sort of capacity on them to do things as well. These just worked, so we were going to look at the bigger ones to actually do a lot more debugging and things like that, but we'll have to see. We just want these to work first and then see how we go. Okay.
Are you using closure as your test bed? I don't think it even works in various things.
Closure is a good one, like with the weight states and things like that, because if you haven't got the right weight state and there's some things off, you get that. There's all sorts of things. We found it for the shifter one. There's so many things that don't go quite right. So there's a lot, but there's many different things. Like Gebench is one to show like things working, but there's a lot of programs that either looking at the traces to see what's happening and the timings are right and the clocks are in sync and they're locked and things like that. But yeah, as you saw, Cyprian created those test splitter to show this is what it's doing. If it doesn't do it correctly, the pattern will be wrong and things like that. I don't know. How can you actually say it's a truly the same, as a blitter or whatever? You can run all these different things. Hopefully they'll all get to a point where we can get it all working like that. But things like closures had hacks and things like that to get it to work and do some special stuff.
Just to add, the weight states will actually be adjustable on these cores as well, so you can give it whatever weight state you want. So if one particular program like Closure needs weight state 4, then that can actually be set in the cores to run like that. Or things like Spectrum 512, if they need weight state 2 specifically, be able to switch the cores to weight state 2. So it should cover everything.
And what about like having each chip set compared to non? I mean, is there variations there with like clock time and differences? Coming from a normal ST point of view.
Yeah. Like Icky was saying, the things like the shifter, I think has 2 weight states, the glue has 2, and the MMU has 2. But when everything's built into the Nexus, you can actually program in whatever weight state you want. So whatever variation on machine that is on the ST range, you can actually program it to do it on that board. So it should literally do everything fine. I believe that was actually put into one of the latest cores of the Mist, if I remember rightly, from what Eagle was saying. So it is actually already a feature out there, so hopefully it'll all work fine.
So, which versions of the ST will this work on? Will it work on original main boards? Or is it going to be restricted to H4 and H5, or just H5?
These are restricted to an H4 and H5 because they're the PLCC socket output, but there's no reason why a board spin couldn't bring it out there. But we've just been developing to this board, so forth. But yeah, because I guess if you were to do something on an original board, either you have to take the funky socket out and have something to be able to put into it and so forth. I think that the shifter is one that's probably going to be easier to replace because it's just a normal, dill and so forth. Okay.
I'm going to add extra features, and you want to get buy-in from the software creators. Have you approached the people like the Atari software emulator writers to say, right, can you make it have a Phoenix mode so that people can run the software developed for Phoenix?
That's an interesting question.
Nicholas is a very nice guy, and if he thought there was traction, he'd help.
Yeah, there's not many writers of software for the ST like there is in the Amiga world. Yeah, but to be able to have these features used and utilized, we'd need to publish how it works, what those features are, so people can actually program to those and so forth. So, yeah, the more that we can provide that, and I guess we'd have to, provide some freebies maybe to some of the developers to help them develop this extra features.
Or you could take out the limits in the source code and push it upstream, so that you could test your 32 meg MMU, and you got it working, and then change the tower rate, push it upstream.
It's interesting. Yeah, it's something it's probably a discussion point really on the forum we should have. Yeah, because ideally, we build these things, we want to take this forward, but it's not going to work if we don't have people developing stuff for it.
You'll find that people who do write this stuff, the first thing they do is they try it on their emulator. They want everyone to use it on the real hardware, but it's at their loft.
Yeah.
But some of it is also just will happen out of the box. If you have a higher bus rate, like you've seen, there's a 16 megahertz hack for this. I know it doesn't work very well. We did it on the the Alpha originally. I think I did it with you. You helped me through it. I got it working, and it worked, and it was really responsive system. So if you get it working at 32, it's going to be a responsive system. As a base system, it might be on par with, dare I say it, a Falcon or a TT or something, because it's got a faster bus. But again, it's these extra features. If you want to unlock those, you're going to have some software to do it.
No one thing for everybody will be, can you put it back to the standard timing so that you can still play the demos that require
that would be
cycle
good,
actor and everything.
Ideally, you want to be able to do that, to drop it back down to original or have it up at the all bells and whistles version.
Wouldn't matter if you had to reflash it.
Yeah. Okay. Good points. Any other questions?
Michael, if you add all these features in, how much will it knock out the existing software?
You don't know. Extra features might not be realized enough that it would still work. It depends what the features are. So for example, if you were to take the MMU and unlock the 14 meg of RAM that's available that's addressable for an ST, you're giving it 14 RAM, it should work. Some programs won't because they expect to be in the 512 or the 1 meg range. I know there's been hacks on programs to be able to do them and so forth, but if it's running with 14 meg RAM, it might not run some software.
There's compatibility between 2 and 4 meg.
Yeah.
Anybody who's got 4 meg will find lots of things crash because nobody expected anybody to ever have 4 meg. And so they put things in shadow and duplicate, and then so you put 4 meg there, that will work.
Yeah.
So it just depends on what the feature is and what you're trying to do with it.
Presumably most things, if you don't use them, it won't make any difference.
Sure.
So if you extend the function of the splitter, if no one calls it, it still work like the other one.
Yeah, that's right. If you extend it, if no one calls it, But if you up the speed of it, then that should make a difference. You should see that. So it's different what you mean by feature or
changing the speed, or everything's timed. They don't wait for the glittering job to finish. They time it. respect to instructions. And so the glitter doesn't finish after 10 instructions, or it finishes before any instructions. Unfortunately, that's how everything was written back then.
Yeah, I think you've been talking to Igor quite a lot about that.
Yeah, this is why we're doing the cycle accurate course to start with. That's what Icky's demonstrating here, because we want 100% recreation of the actual original chipsets. So anything original Atari can do, we can do on the recreations. But say the Nexus is where instead of having little 3 boards plugged in, it's just all plugged into one. But say the way to look at it is it's more like whereas an accelerator only accelerates its own memory, for example. This actually accelerates the whole bus, so technically it's like a super accelerator. And also the blitter, I've been talking to Igor in the background, and the blitter will have like full speed access to the SD RAM. So if the bus is say at 32 megahertz, you could actually probably run the blitter at something like 128 megahertz. So it's going to be a massive speed gain on virtually any application you use, and including games if you use the blitter.
Would it be possible to just have a register in memory that the machine boots up in standard mode, and you have, say, a desktop accessory that then switches to the enhanced modes?
That could be feasible. we did something similar with the flashy clock board that we had. So we had a memory address in there with the shift. I think I put it in the shifter because there's a spare address there, and we actually multiplexed it. That's when we were talking with SMON, and we were able to use that flashy clock to be able to run a slightly modified version of TOS, and you could change any TOS as well, whatever. But effectively, we were able to take out or add in so that you had low, medium, and high, because in using the shifter that we had, you didn't need to swap over the monitors. And they were able to, we had scanline ones in, had another dialog box to choose the different ROMs, because we had the different ROMs as well, and so forth. So yeah, it's feasible. All these things are feasible, but it's down to software. And
I was just thinking to make it a more compatible by default, but easily changeable without jumping around.
That would be the aim, to do that, yeah. Because if you can just flick a register in memory, like I say, default machine or super fast speed, it's like turning an accelerator on and off, basically. Yeah, we should be able to sort that out. Yeah.
Well, I've seen to pick up a few accelerators and booster bits and bobs that have been made recently. And the way they go about it is to write a magic sequence which unlocks the extra registers. So in which case, if you had something that worked on the older machine, it was just write that code sequence in, and it worked as normal. But if you wanted the extra features, then it adds extra mapping and use mapping memory.
Different ways we can do it.
I think that's what we'll need to do that if you don't have any memory space, address space left. How else are you going to add these switches if there's no memory address space left?
I don't think it'd be a problem. If you're only talking one register or just one word or something, you've got 16 bits to turn features on and off, so you don't need any memory, just one word in memory, in memory map.
yeah. Okay. Any other questions?
When can I buy one? Sorry, when can I buy one?
No idea. Look, yeah, we are. These are the first boards that have worked. We were actually surprised how well they worked. We now just need to work through the cores and get them 100% with Igor, and then we should be in a place to sort of say, well, we can now do the original chips. Then that gives us the springboard for Nexus, and then move on from there. So we'll see how it goes. I also need to work with Igor on the shifter, because that's also that closure on the shifter is really causing me pain in the ass. Sorry? It's I think it's the bit planes are all out on it for some reason. I'm not sure. I haven't looked at this for about 2 years because I've been out of the game for a while, but you know, I need to get back into it. Yeah. Cool.
How's your keyboard development going on?
Again, I've not been doing much for bed, so that one I've got ideas on that. Yeah, I've got ideas with that one. So. All right. Anything else? Okay, cool. Thank you.